Hello everybody, this is Mika Seppälä. In this video, I explain how to compute volumes of solids obtained by letting a domain under the graph of a function rotate around the x-axis or around the y-axis. Such solids are called solids of revolution. Their volumes can be computed by integration. Letting the domain bounded by the graph of a function f rotate around the x-axis, we get a solid of revolution. Here on the left we see the graph of the function f, and on the right we see a picture of this corresponding solid of revolution. Our task is to determine the volume of this solid of revolution, and now these volumes can be computed by definite integrals. In order to be able to do this, we have to relate this solid to certain Riemann sums. Therefore, we start by considering a Riemann sum approximation for the domain under the graph of the function f. Here this picture shows an illustration of these Riemann sums. This picture shows a left rule Riemann sum approximation for the domain under the graph of f. This approximation consists of rectangles placed over subintervals of this interval of integration. Now, if we let each one of these rectangles rotate around the x-axis, we get of each rectangle a cylinder. And these cylinders then approximate the solid of revolution. So letting these cylinders approximate the solid of revolution, we get a formula for the volume of this solid. In order to find the formula, we need to be a little bit more specific. Now let the x interval from a to b correspond to this solid. We decompose that interval into n subintervals of equal length, where n is a positive integer. Then each one of these subintervals has the length delta of x, which equals b minus a divided by n. Now in the Riemann sum approximation of the domain under the graph of f, the kth rectangle has as its height the value of the function f at the left endpoint of the kth subinterval, that is at the point xk minus 1. Therefore, the volume of the cylinder is base of the cylinder times height. Now height of the cylinder is delta of x. The base of the cylinder is going to be a disk of radius f at xk minus 1. That is a disk which is the same as the height of this kth rectangle. Therefore, the volume of this kth cylinder vk is the area of the base, that is the area of the disk of radius f at xk minus 1 times the height of the cylinder. So we get pi times f at xk minus 1 squared times delta of x. So this is the volume of one approximating cylinder. Now we take all approximating cylinders, therefore we have to take a sum as k goes from 1 to n of these quantities pi times f at xk minus 1 squared delta of x. And this now looks like a Riemann sum. For computational convenience, we may want to bring pi outside of summation and therefore also outside of integration. That we of course may do, and therefore we conclude that the approximation for this solid of revolution has the volume pi times summation k from 1 to n function f at xk minus 1 squared delta of x. But this approximation is a Riemann sum for the integral pi times integral from a to b f of x squared dx. Therefore, we conclude that the volume of this solid of revolution is pi times integral from a to b f of x squared dx. This is the volume formula. Now observe that if we slice the solid of revolution by a plane perpendicular to x-axis, we get a slice which is a disk. The radius of such a disk is the value of the function f at the intersection point x. That's at the point where we form the slice. Now, the area of this disk is pi times f of x squared. Of course, pi times radius squared. And therefore, in this volume formula, we really integrate the area of a slice. And this observation can be generalized, and volumes in general can be computed by slicing the solid in question in a suitable way and integrating the areas of these slices, and hence get the volume of the solid. So for solids of revolution, the volume formula is volume equals integral from a to b, pi times f of x squared dx, and of course this constant pi can be taken also outside of integration. Now let us use the volume formula to compute the volume of a ball of radius r. Such a ball is obtained by letting a half disk of radius r rotate around the x-axis. We take the upper half of a disk bounded by the circle x squared plus y squared equals r squared, and you solve y out of that, you get y equals positive square root of r squared minus x squared. This is the upper half of this circle, and it bounds a disk, half disk, which rotates around the x-axis and forms the ball of radius r. Now, by the volume formula, the volume of this ball of radius r is pi times integral from negative r to r f of x squared dx. That is pi times integral from negative r to r square root of r squared minus x squared, and that's squared dx. But square root squared is simply the expression under the square root, and therefore the volume is pi times integral from negative r to r squared minus x squared dx. And this is now simple to compute because we simply integrate the polynomial. Integral of r squared with respect to x, an antiderivative, is r squared times x. An antiderivative of negative x squared is negative x cubed over 3. We substitute from negative r to r. And we get that the volume is pi times from the upper limit r cubed minus r cubed over 3. And then we subtract what we get from the lower limit. We substitute in place of x and negative r. We get r squared times x is minus r cubed. And then we still have minus r cubed over 3. And now this simplifies to 4 times pi divided by 3 r cubed. So this is the familiar formula for the volume of a ball. One may also observe that the volume of a ball is roughly about half of the box containing the ball. That may be easier to remember. Anyway, the volume is precisely 4 times pi divided by 3 r cubed. The circle x squared plus y minus 2 squared equals 1 has as its center the y-axis point 2. And its radius is 1, therefore this circle lies completely above the x-axis. If the disk bounded by this circle rotates around the x-axis, we get a solid torus, shown here on the right below the disk. Now our task is to compute the volume of this torus using the methods just developed. Now we have a slight problem here because the domain that rotates around the x-axis is not a domain under the graph of a function, but it is rather a disk lying completely above the x-axis. For that reason, we have to do this in 2 steps. We first let the yellow domain indicated here on the picture rotate around the x-axis. When we do that, then we get this red solid disk pictured below. Now the torus had a hole. This red solid disk does not. We have to carve a hole to this red solid disk, and we do that by letting the domain, now indicated by yellow here in the picture on the right, rotate around the x-axis. Then we get a different solid of revolution, and this solid of revolution corresponds to the hole of the torus. So we observe that this torus for which we have to compute the volume is this big 3-dimensional solid red disk minus the hole. That is the torus. And for this three-dimensional solid disk on the left, we can compute the volume, and for the hole, we can also compute the volume using the methods that we have now developed. So this is the plan for what we do. The circle that bounded the two-dimensional disk that then rotates around the x-axis and forms the torus was given by the equation x squared plus y minus 2 squared equals 1. Solving y in terms of x out of this equation, we get y equals 2 plus or minus square root 1 minus x squared. The choice plus for the square root corresponds to the upper half of this circle. Therefore, the yellow domain indicated in this picture is the domain under the graph of the function 2 plus square root 1 minus x squared. When that yellow domain rotates around the x-axis, it yields a three-dimensional solid red disk shown here below this domain. And by the formula that we have just developed, this volume of this three-dimensional red solid disk is integral from -1 to 1 pi times 2 plus square root of 1 minus x squared, and that's squared dx. This, of course, can also be written as pi times integral from -1 to 1. So this pi comes out of integration, and then we expand 2 plus square root 1 minus x squared, and that's sum squared. When we expand that, we get 4 plus 2 times 2 times square root of 1 minus x squared, that is 4 times square root 1 minus x squared, plus square root of 1 minus x squared, and that's squared. That yields simply 1 minus x squared. And then we integrate with respect to x, so we write dx in the end of the formula. So this is the volume of this solid red three-dimensional disk. Now we have to deal with the hole. The hole is now obtained by letting the yellow domain under the graph of the function 2 minus square root minus 1 minus x squared rotate around the x-axis. The volume of this solid is integral from -1 to 1 pi times the quantity 2 minus square root of 1 minus x squared, and that's squared dx. Now again we take pi outside of integration and we expand the product. We get that the volume V2, the volume of the hole, is pi times integral from -1 to 1 4 minus 4 times square root 1 minus x squared plus 1 minus x squared dx. So our strategy is to compute the volume of the torus in two steps. First, we compute the volume of the big solid three-dimensional red disk that contains both the torus and its hole. And then we subtract from that the volume corresponding to the hole. And that difference is going to be the volume of the torus. So the volume of the torus is the difference of these two volumes for which we already have computed expressions. So V equals V1 minus V2. That is V equals pi times integral from -1 to 1 of the expression 4 plus 4 times square root 1 minus x squared plus 1 minus x squared. And then we integrate with respect to x, so we write dx in the end. And then we subtract from that pi times integral from -1 to 1. And then we integrate almost the same expression, except the sign in front of the square root expression is now changed. So we integrate 4 minus 4 times square root of 1 minus x squared plus 1 minus x squared instead of 4 plus 4 times square root and so forth. So when we do this computation, then we observe that this 4 cancels out, because we first have integral from -1 to 1, 4, and then we subtract from that integral from -1 to 1 of 4. So they cancel out, and so do this part 1 minus x squared. And we are left with 8 times pi times integral from -1 to 1 square root 1 minus x squared dx. Here we have moved the coefficient 8 outside of integration from inside the integration. That we may of course do. And now for computational convenience, it is good to observe that integral from -1 to 1 of square root 1 minus x squared dx is 2 times integral from 0 to 1 of square root 1 minus x squared dx, because the function 1 minus x squared is even. So because of symmetry, we can simplify the integration so that we integrate only from 0 to 1. When we do that, we have to multiply the whole expression by 2. So we have observed that the volume that we have to compute is now 16 pi times integral from 0 to 1 square root 1 minus x squared dx. And here we substitute x equals sine of t. When we do that, then dx equals cosine of t dt. And we also have to compute the new limits for the integral. When x equals 0, we solve t out of the equation 0 equals sine of t. We get t equals 0. When x equals 1, we solve t out of the equation 1 equals sine of t. We get t equals pi over 2. Therefore, this volume, which now is integral of 16 pi times integral of from 0 to 1 square root 1 minus x squared dx, gets the form 16 pi times integral from 0 to pi over 2 of square root 1 minus sine squared of t times cosine of t dt. And now 1 minus sine squared is cosine squared. Square root of that is just cosine. So we really have to integrate cosine squared of t dt. So the volume is 16 pi times integral from 0 to pi over 2 of cosine squared t dt. Here we use the double angle formula. Cosine squared of t is 1 plus cosine at 2t divided by 2. Therefore the volume now gets the form 16 times pi times integral from 0 to pi over 2 of the expression 1 plus cosine at 2t divided by 2 dt. And now this 2 in the denominator of the integrand, of course, can be taken outside of integration, and we really have just a formula for the volume, which is 8 times pi times integral from 0 to pi over 2 of 1 plus cosine at 2t dt. And this last expression is easy to integrate, because an antiderivative of 1 plus cosine of 2t is t plus sine at 2t divided by 2. And then we substitute from 0 to pi over 2. When we substitute the lower limit, we get 0. Then t is 0, and sine at 2t is sine at 0, which is also 0. When we substitute the upper limit, the sine term gives us sine at 2 times pi over 2, which is sine at pi, which is also 0. So the only quantity that contributes to this integral is this term t, and at the upper limit the value is then pi over 2. And therefore the substitution yields 8 times pi over 2, which simplifies to 4 times pi squared. So this is the volume of this torus, 4 times pi squared. So our answer now is that the volume of the torus in question is 4 times pi squared. And we computed that in 2 steps. We first let the domain under the upper half of this circle rotate around the x-axis. That yields the big solid 3-dimensional disk shown here in the middle. And then we subtract from that the volume of the whole of the torus. And that is the volume of the solid of revolution obtained by letting the domain under this circle rotate around the x-axis. And the difference of these two volumes is the volume of the torus in question. A remark should be made at the point where we had that the volume of the torus is 8 times pi times integral from -1 to 1 square root 1 minus x squared dx. We could have simply observed that this integral from -1 to 1 square root 1 minus x squared dx is the area of the yellow half disk of radius 1. Now the area of a disk of radius 1 is pi times 1 squared, that is pi. Therefore the area of a half disk of radius 1 is pi over 2, and we could have simply concluded that the volume of the torus, which is 8 times pi times integral from -1 to 1 square root 1 minus x squared dx, is 8 times pi over 2, which is 4 times pi squared. That is the result we computed in the long way. So as a summary, let me now recall that we have derived the volume formula v equals pi times integral from a to b f of x squared dx. This is the volume of the solid of revolution obtained by letting the domain between the graph of the function f and the x-axis interval from a to b rotate around the x-axis. All these volumes can be computed by this formula.